Hello, so today we are doing this problem called is graph bipartite from Leetcode. It's a medium problem, and so let's get to it. So the problem says we have an undirected graph and we want to return true if and only if it's bipartite. And basically a graph is bipartite if we can split the set of nodes into two independent sets. Let's call one A and the other one B, such that every edge in the graph has, so basically we can kind of construct let's say something like x1, or let's call it a1 node, and then a2 node, and then a3 node, and this set is like the first set, and so something like this. And so this set, and then on the other side we can have another set, and let's say b2 and b3, and this is set b, and the only connection that exists are between these two sets. So something like this, these two are connected, and then these two are connected, and then these two are connected. And if we find a graph, and this can be like more than just three, but the idea is that there is one set, there are only two sets, and the connections that exist are only between elements from two different sets. And so every edge in the graph has one node in A and another node in B. That's the problem. So this problem here, we get the input is graph I, which is a list of indices basically that represent the connections. So this says that one is connected to so basically says that 0 is connected to 2. Well, I guess this input is a little bit weird, but basically is the position actually. So here the elements at positions, but this input I think needs a little bit more explanation, so let me just take it like this and explain it. So this is position 0, and this is position 1, and this is position 2, and this is position 3. And basically the way this input works is that this means that 0 is connected to 1 and 3, 1 is connected to 0 and 2, and 2 is connected to 1 and 3, and 3 is connected to 0 and 2. So basically the index represents the node, and the value represents the neighbors, or the values that it's going to. So for example, here we have this because you can see that that 0 is connected to 1 and 0 is connected to 3 because of this, and 1 is connected to 0 and it's connected to 2 because of this. And yeah, you get the idea. And this one, it can be bipartite because if we look, we can put 0 here, and 0 is connected to 1, and we can put let's say 2, and 2 is connected to 3, and now 0 is not connected to 2, 1 is not connected to 3, and basically 0 is connected to 3 though, right? So yeah, actually this is not the way I should do it. So 0, 1, let's say, and then here I'm just going to organize them in a way similar to this so that we can see both sets, and here 3. So we know that 0 is connected to, there is an edge between 0 and 1, which is this one, and there is an edge between between 0 and 3, and there is an edge between so actually let me just and there is an edge between 0 and, is there an edge between 0 and 2? No. Is there an edge between 1 and 3? No. And so yeah, these are, and so this is our set A, and this is our set B. And there is no connection between the elements of the set themselves. There is only connection between the elements of one set to the other, right? And so Bipartite asks us to check if we can decompose the graph into two sets such that one has edges only in the other sets, and that's the way it goes. And so how can we do this? So we can color just color the graph using basically BFS or DFS, but use only two colors. And the way we are going to do the coloring is that color a node with, let's say we color a node with blue, then its neighbors gets colored with a different color. Let's say, for example, red, for example, here, right? So that way, if we do this, that means that if every color and the nodes connected to it should have a different color, that means once we did and finished BFS or whatever traversal we are doing, then the colors, then the result of traversal and coloring is that no edge has two nodes of the same color, because if an edge has nodes of the same color, that means they are in the same set, which means that it's something like this. They are connected, which means we broke the rule of no elements from the same sets are colored. And so that's what we are going to do, is we are going to pick a color and then pick two colors and then color these color edges, nodes of each edge with different colors. And every time if we encounter a neighbor of a node that has the same color as the one we are trying to color the node with, then it's not bipartite. And if we go through the entire thing and we are able to color with this constraint, then that means the graph is bipartite, right? And so in order to do this, we need just to have a color map that kind of that saves which node was that saves the color that was assigned to the node. And yeah, that's pretty much all there is to it. So let's just create our color map, and then we know that the nodes, it says that the nodes are from 0 to the length of the graph, -1. And so that's what we are going to do. So we have node in range of length of the graph. This would go from 0 to n-1 with Python. And so we are doing this because the graph, it says here that so the graph may be disconnected. It doesn't say that the graph is all connected. So we may have a node that we don't visit when we start from, like, let's say this node. There may be other nodes in another component in the graph. And so we do this loop so that we can go to these also. And so we start our DFS. Let's say here, we start our DFS from that, and let's do our DFS. Actually, let's do our DFS inline here. So this is our DFS, and DFS, let's do it iteratively. So that would mean we have a stack. And the stack will contain a node first, and we'll go through the stack while it's not empty. And then we would color, give the node a color. So what I will be doing is that, let's say blue, I will represent that by the value 0. And then red, I will represent that by the value 1. And this way, if I want to if I'm at a node with colored with blue, then that means that adjacent nodes should be colored with red, which is equal to 1 minus blue. Since blue is 0, to get 1, I just do 1 minus 0, and the reverse with, if the node was red, then if I do 1 minus 1, which is 1 minus red, I get 1 minus 1, which is 0, which is the color blue. And so this allows me to easily switch between the colors. And so first I'm going to color this blue, and so that would be 0, right? And then I'm going to go through the stack, and then I will pop the node from the stack. Let's say n, call a node. That would be stack.pop. And I'm going to go through the neighbor, or let's call them a neighbor actually, and just a graph. So we know that the graphs are indexed with their value. So if I do graph 0, I will get the adjacent nodes to that node, and so I can just do graph node. And what I will do next is I will check if the neighbor is not in color. That means we haven't colored it yet, so that's fine. That means we can color it. And so to color it, we are just going to say that color of neighbor is going to be different. So every node, we color its adjacent node with a different color. So that would mean 1 minus the color of the node. And then we will need to add it to the stack, right? So that would mean stack append neighbor, so that its own neighbors also get explored. Now, otherwise, if we have a node where its adjacent node is already colored, we need to check if it has the same color, because if it has the same color, that means we violated the bipartite condition. If it has a different color, then that's fine, we don't care, right? So we can just check if color of neighbor is equal to the color of node. We can return false. And that's pretty much it. So actually we can just say here, reduce this like this, and otherwise we can just return true. So basically we return true if we didn't find any nodes that violate the bipartite condition. That means we are good, and we can return true. And yeah, so that's pretty much it. We have the map, we have our color, we started DFS here. And so one other thing that we can do is we shouldn't need to explore a node that was already colored here. So we need to check. So this also acts, the color map, you can notice here, acts as visited set that allows us to not revisit nodes multiple times, because whenever we visit something, we color it. And so we can just here check if the node, only if the node is not in color, then we can try to process it with DFS, and that would mean this, and that's pretty much it. So we check if not in color. This is usually equivalent to not in visited that we usually do for DFS. So we start our DFS process here. So our DFS process is now here, which consists of creating a stack with the start node, coloring that node, which is also equivalent to adding it to visited, and then going through the stack, taking the node out, exploring the neighbors. If a neighbor is not colored yet, we can just color it. There is no condition of bipartiteness is violated yet. We add it to the stack. But if it's already in the color map, that means it was already colored by something else. So we check that we don't have the same color, because if we have the same color, that means it's in the same set, and that means there is an edge between two nodes in the same set, and so we return false. Otherwise, we just return true. So let's try this. There is no is, it's just not in color. Say no. Okay, so that passes there. Let's submit and see. Okay, so that solution passes. Now there is nothing that, so here I've done it with iterative DFS. It's just a good idea to always try to do it with the recursive DFS to get used to it. And so to do it with iterative DFS, I can just say, instead of doing this, I will just do this check right away here. So no more iterative DFS, but the rest of the template is the same. And so here, if the node was in color, I'm going to check. And so I'm going to check if the color of the node Actually, let me do that later. And so we check if it's not in color, then we color it, right? And we set its color to 0, and then we explore it with the DFS. So we explore the node with DFS. And if the result from that DFS says that it's not bipartite, then we return false. Otherwise, we explored all nodes and they all said that it's bipartite, and so we return true. So let's define our DFS node. So this DFS is to check if graph from that node is bipartite, right? Or let's say or colored correctly, because that's essentially what we are checking. And so how do we do that? So we need to go through the neighbors of that node, same way we did with DFS, with the iterative DFS. And then we are going to check if that neighbor is, if not in color, then we can just color it. There is no problem. And so we can just color it by doing color neighbor is equal to the opposite of the current node's color, which is just minus color node. And then we need to do DFS on that neighbor. Otherwise, we need to check if the color that it has is equal to the color of the current node, then that means we have a problem. We can return false. That means that two adjacent nodes are in the same set, right? And so otherwise, if we didn't find anything like that, we can return true. And so this is the same way, except instead of using a stack and appending to it, we are just using a recursive call to a DFS function. Okay, so it passes there. Let's submit. Okay, so we have a wrong answer in here. Let's see where did we, a little bit further this case, or let's see what we did wrong. So we are coloring the neighbor with 1 minus color of node. That's correct. But yep, so one thing is the problem is here. So we should check if the DFS of the neighbor also returned false and return false. And that we are not doing that, which is bad here. Because whenever we encounter something that tells us like the rest of my neighbors are not, like don't verify are not colored correctly, then that means that the graph is not bipartite and we need to return false. And yeah. Let's take this test case and run it on. Okay, so that works on that test case. Let's see if this passes. Okay, it does pass. Cool. Now we did it with DFS iteratively and recursive. Let's try to do it with DFS, with BFS actually, because still it's the same traversal. The only thing that we are interested in is coloring, and if the color of adjacent nodes are the same, then we return false. So nothing prevents us from doing that with BFS. It's essentially also BFS checks the neighbors of each node, so we can do it with BFS. So let's do that. Okay, this is a little bit too small. Okay, cool. So let's do a BFS here. We don't need this anymore. So with BFS, we need the usual template, the same template that we did for DFS, so that we can go through all the nodes if we have a graph that contains multiple components that are not connected. And so we need to go through the nodes in the graph. And so that means node in range of length of the graph, so that's still the same. And we need to have our color map, right? And we need to check now. We need to check if node not in color, so that we don't color it if it was already colored. In that case, we need to start our BFS, which means let's do a queue, which is in Python. Let's just do collections of DQ. And the start point of that would be node. And then while a queue, we need to color the node, so that would mean color of node would be equal to 0. and then we would pop the node by doing q.pop. And then we will need to go through the neighbors of that node the same way we did with DFS. And then we'll need to check if it's colored or not. So if neighbor is not in color, it's not colored yet, so there is no problem. So we can just say the color of the neighbor is the opposite. If the neighbor was colored, if the node was colored blue, we need to color the neighbor with red, with a different color. So we do that with this. And we need to add the neighbor to the queue, so its own neighbors get also processed. Otherwise, if the neighbor was already colored, then we need to check if it's colored with the same color as the node, because in that case, that means they are in the same set and they are connected. And so we need to check if neighbor is equal to color of node. Then we need to return false, because this means we can't color properly to achieve a bipartite graph. And otherwise, if we went through all of this and didn't find any problem, we can return true. And yep, that should be enough. Let's run this. Cool. Let's submit it. Okay, so that also passes. So you can see it can be solved with BFS, DFS, and the insight I think from this problem is using auxiliary data structure with the traversal, so that it can help you make some decisions and annotate nodes with some data so that you can use it later. So the same mechanism can be done by storing patterns, can be done by storing more than just the colors, so that you can do some processing here, or you can check some property on the graph. And yeah, so it's not, when we are doing the traversal with BFS or DFS, we are not limited to just the template that we usually use. We can use more other data structures to achieve whatever checks we are doing. And yeah, that's it for this problem. See you next time. Bye.